Hi, welcome to this video series on cryptography. Today I'm going to talk about quadratic residue of composite numbers. This particular problem related to quadratic residue has many applications in cryptography. We have seen quadratic residue of prime groups, right? We saw ZP star, for example, right? Um, P is a prime number, and we looked at quadratic residue of elements in this particular group. Okay. In this video, I'm going to generalize it to Zn star, right? What is Zn star? Zn star is made of all elements from 1 through n, such that GCD of, okay, let me write it like this, right? Such that GCD of x comma n is 1, okay? And of course, x has to be less than n and greater than or equal to 1. Okay, so all these elements, right, are basically what contains what makes the group Zn star. Okay, all right, so this is basically the definition of Zn star. GCD is the greatest common divisor. All right, so how do we compute quadratic residue for this particular group? So you usually don't compute a quadratic residue for a group, you compute for an element. So how do we define a quadratic residue? From a ZP star discussion, we probably may recall that an element y is considered a quadratic residue if we find another element x such that x square is equal to y. For example, we could say, let's say, for example, our P is 5 for a moment, okay? Then, of course, 4 is a quadratic residue because 4 can be written as 2 power 2. So if an element can be written as power of 2, then we say y is a quadratic residue, right? This is y. This is a quadratic residue. And the x is the square root of y, because when you multiply x 2 times, we get y, okay? Y is quadratic residue, x is the square root, okay? This is the definition that is also applicable independent of whether we work with ZP star group or Zn star, okay? So we are going to study the structure of quadratic residue in the context of Zn star for a few cryptographic systems. For example, Goldwasser-Mikli system or homomorphic encryptions that are based on those. Okay. So it turned out that the Zn star group have interesting properties that actually make the problem of computing quadratic residue much more challenging, which we are going to use to build new crypto systems. Okay, probabilistic encryption systems can be built using the property. So it's difficult to tell whether a number is a quadratic residue or not in Zn star. That is the problem that has been used to construct crypto systems. Okay, first let's get straight into Zn star and do some little numeric examples to get this idea across. Okay, so for that purpose, I built a small program, right, and which I'm going to share with you now, and we will directly execute this and play with it a little bit. Okay, so I'm going to straight away start the Python interpreter, right, and I wrote my little quadratic residue algorithm, which I will show you later. So it will print the residue table. Let's start with ZP star very quickly. Let's take P to be 5, for example, okay? So we will do residue of P. So, okay, what you see is a small table, right? There are 4 columns, right? And as you may remember, Z star P is made of elements from 1 through 4, right? 1, 2, 3, 4. The second column is what we are interested in to study. For example, 4 is a quadratic residue because 4 can be represented as 2 square. Okay, so that is one of the important things to remember. 4 is nothing but 2 square. Okay, and what about 4 has another root also. 3 square is same as 4 in mod P, right? Because 3 square is 9. 9 mod 5 is 4. So we get to know that 4 has 2 roots. Okay, what are the roots of 4? Number 3 is one root, right? Another root is number 2. Okay, so what about other elements on this column number 2 that I want to talk about? We have element number 1, right? Element number 1 also occurs 2 times. I don't print the same thing, so you can assume this 1 here. 1 has element root 1, but 1 also has root 4 because 4 square is 16, 16 mod 5 is 1. So through this example, we can, I mean, this is not a proof, but it's not difficult to prove that every element that is a quadratic residue has 2 roots. Actually, we can even try other examples just to convince ourselves that's the case, right? Let's say quickly set the P to be say 7, right? All you're seeing now is that quadratic residues are elements 1, 2, 4 because they can be written as power of other element by 2. Okay, they are power of 2. For example, 2 is a quadratic residue, although in the real in the set of integers 2 cannot be represented as power of 2, right? But in the case of prime group, it's possible. 2 can be represented as 3 square, which is 9. 9 mod 7 is 2. Okay, so as you can see here, 2 occurs 2 times on the, across the second column, right? This is basically the set of quadratic residues, and it tells us that each element occurs 2 times in this list. You can imagine here is 1. Okay, so that's interesting property for prime. Now let's look at composite numbers. So composite numbers are what type of numbers I'm interested in. Composite numbers are of the form n equal to p times q, right? And I assume p and q are both distinct primes, right? And they both are odd primes. Okay, so when I say odd primes, it has to be at least 3, right? P and q are both odd primes, and they are different to each other. So let's consider those kinds of groups and look at quadratic residues in such groups. Okay, so very quickly, let's say my p to be 3 and q to be 5, right? What is my n? N is p times q, so it should be 15. So let's study the quadratic residue for z star 15. Okay, so residue of 15. So what you're seeing here is, again, column number 2 is interesting for us because of quadratic residue is modeled there. What are the quadratic residue in this group? The quadratic residues are elements 1 and 4. Okay, I'll put a 1 here for completeness, right? 1 and 4 are the only quadratic residues. It makes sense because first of all, we can check quickly. 4 is naturally quadratic residue because it can be written as 2 power 2. Interestingly, 4 also has other root called 7 because 7 square is also same as 49, which is same as 4 mod 15, right? So 7 is also another root of 4. What about other numbers? We can quickly check that 8 is also a root of 4 because 8, you can see here 8 square is nothing but 4 in this group z star 15, right? And what about the other roots? So we have these 2 non-trivial roots, right? But then we have trivial roots like 1 square, obviously. Oh, sorry, not 1, but I'm talking about 4. 2 square, this is 1. And this is the second one, third one, and this is the fourth one. 13 into 13 is 169. 169 is congruent to 4 mod 15, right? Because it will fit in 165. Okay, so what we are seeing here is that it looks like every element will have 4 roots in the quadratic residue in the context of z star 15, for example. Okay, let's try to see whether that pattern holds true for other numbers. Okay, so let me quickly change my p and q, right, and make it so say my p is 3 and q is 7. Okay, now let's consider my n 21 and let's print the table for 21. Okay, so now what are the quadratic residues? The quadratic residues are well, I'll put a 1 here because I stop, as I said, after the 1. So 1, 4, 16. So the quadratic residues are 1, 4, 16. These are the 3 quadratic residues of the group z star 21. Okay, z star 21 is the group that I'm playing with, right, in this case. And we confirmed that these are the 3 quadratic residues, which is easy to see because 4 can be written as 2 square, 16 can be written as 4 square. But the question is, are there other roots, right? We can check that. Let's take number 1. How many roots of 1? Of course, 1 for 1, very trivial. Interestingly, even 8 is the square root of 1 because 8 square is 64, 64, when you do mod 21, you get remainder 1. Okay, so this is the second root. And 13 into 13 is 169, which is also mod 21 will give you 1. And 20 into 20 is 400. You can check for yourself. I mean, I have a computer in front, so I can also quickly check. Let me do this right. What is 20 into 10? 20. 20 power 20 power 2, not 20 into 20. Yeah, okay, both are same anyways. So print 20, there's a power function, 20 power 2, right? Mod n, right? N is 21 in our case. So as you can see, you get 1. All right. So what my point is that it seems that each element here has 4 roots. We can check for 4. 4, of course, is 2 square. 5 square is also 4 because 5 square is 25, mod 21 is 4. And not necessarily trivial is 16. 16 power 2, we can check it quickly. 16 power 2 is also 4, which is very nice. And 19 power 4 turned out to be 19 power 2 rather, also turned out to be 4. That means we have 4 roots for number 4, and we can check also the same for 16. So anyway, so what you're seeing here is that if an element is quadratic residue, it has 4 roots in the case of Zn star, as opposed to 2 roots that we saw in regular prime numbers. Okay, that's basically the main message. The main message is that I will summarize it quickly. We saw in the context of Zn star, each element has 4 square roots, 4 roots for the elements in the quadratic residue. Okay, when we work with Zn star. Okay, this is basically the main message. This one, the quadratic residue, each element of the quadratic residue has only 2 roots. Okay, so why is this important? We will see next in the next segment of the presentation. I will show you how we can use this concept to build crypto systems. Okay, one important thing before we wrap it up is that it is not easy to check whether a number is a quadratic residue or not in the Zn star context. Okay, that we will use to build a crypto system. It's rather easy in the context of Z star P, because all we need to do is we check whether the legend symbol or equivalently there is something like this. In order to say X is a quadratic residue, all we need to do is check whether X power P minus 1 by 2 is congruent to 1 mod P. If this is true, then we say X is a quadratic residue in the context of Z star P group, right? But remember, we are not working in Z star P anymore. We are trying to work with Z star N group, okay? And there we don't have such a nice formula that will tell whether a number is a quadratic residue or not, okay? So that's a computationally difficult problem, and many crypto systems are built on that assumption. Okay, that's all. Thank you very much for your attention.